Hey, Matthew, how's it going? Ah, fair enough. Whatever you need to do, man. Let's see. Let's turn the fan in here. I'm excited. We're going to do some really good stuff today. You prove the identities, great. So hopefully that will make the punchline of what I'm about to say go down a lot smoother. Those identities are basically responsible for an extremely amazing fact that I'm going to state at the end of this. Do you have any guesses where they came from? Yeah, the things I'm showing you guys today. Yep. UNLV professor? Nope. I am pretty sure no one at UNLV has ever even thought about that identity because um, the things that I'm going to show you today were actually surprising even to Dr. Berrigar when I showed them to him in our elliptic curves class. The meeting ID. Okay, let's see. The meeting ID. I think I include that with the email, but let's see. The meeting ID is here. I'll just type it in the chat. Do you know if Ashrith is going to join us today? The only reason I ask is because the only part that we didn't get to with Ashrith is proving the series for Cinch and Kosh, and the series for Cinch and Kosh are kind of relevant to the motivation of what we're going to be doing. Oh, there he is.
Oh, hello.
Hello.
All right, I can talk. My audio is going to be a little bit scuffed.
Yeah, I understand.
Hello?
Hey, Ashrith, how's it going?
That's good. So we have two Matthews here today.
Yeah. So his new computer doesn't have a mic, so he's using his phone for audio. All right.
Yeah, we're doing a similar thing when we play Apex.
Sorry?
Oh, when we play Apex Legends together, I use my phone as my mic, and I listen to audio through my computer.
I've been seeing a lot the second Matthew lately.
All right, so let me just start out just reviewing how we got the series for sine and cosine. So what we said is that we want sine and cosine to be the coordinate functions of a parameterization of the unit circle. So that means that we would assume that even though we don't know what the series are, they have to satisfy the identity cosine squared of theta plus sine squared of theta is equal to 1. And if we take and we factored that as cosine theta comma sine theta dotted with itself, we took the derivative of that using the product rule. We were able to conclude that its derivative has to be perpendicular to it. So then in Euclidean geometry, the unit counterclockwise perpendicular is given to xy is given by minus y comma x. So then we concluded that cosine, the derivative of cosine is equal to minus sine, and the derivative of sine is equal to cosine. And just using our knowledge of what sine and cosine, their value should be, their initial conditions at 0 should be, we were able to then construct the Taylor series for sine and cosine. Okay, so I'm going to do the same exercise for hyperbolic sine and cosine again, so that we can see just this method, refresh ourselves. And then there's one particular feature of hyperbolic cosine that I want to focus in on. So if we take our usual coordinate xy plane, but we define a new dot product called a Lorentz, or sometimes it's called a Minkowski product, depending on who you're talking to. Like this, where we say that V1 is perpendicular to V2 if and only if V1 Lorentz dot V2 is equal to 0. If we dot a variable vector with itself, and set it equal to a constant, that is the definition of a circle. So we get this. And so now what we are looking for is a parameterization of this hyperbola by functions. I'm going to call them cosh theta, sinh theta. So that cosh of 0 is equal to 1 and sinh of 0 is equal to 0. And so if they're going to parameterize the unit circle, then they have to satisfy this identity, cosh theta squared minus sinh. Oh, what are you doing? Sinh theta squared is equal to 1. And we can factor this as cosh theta comma sinh theta Lorentz dotted with itself, cosh theta comma sinh theta is equal to 1. And so what we're going to do is we're going to take the derivative of this with respect to theta. And according to the product rule, which we're able to use since the hyperbolic dot product, so the Lorentz dot product obeys the distributive law, we conclude that 2 times cosh primed of theta sinh primed of theta Lorentz dotted with cosh theta comma sinh theta is equal to 0. So they're perpendicular to each other. In hyperbolic geometry, a counterclockwise perpendicular to AB is given by B comma A. So what we conclude is that cosh prime theta, it should be sinh theta, and sinh prime theta should be cosh theta. And so from here we get sinh of 0 is equal to 0, sinh primed of 0 is equal to 1, sinh double primed of 0 is equal to 0, and so on. Triple primed is equal to 1, and similarly cosh of 0 is equal to 1, cosh double primed of, primed of 0 is equal to 0, cosh triple or double primed, yep, 0 is equal to 1, cosh triple primed, 0 is equal to 0. So with this information, we can just plug our knowledge of the derivatives into the Taylor series formula to get that sinh of theta should be equal to x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, and so on. And cosh of theta should be equal to 1 plus x squared plus 2, or x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, and so on. All right, so if we look at cosh theta, there's something a little bit unsatisfying about the formulas that we just got for parameterizing the unit hyperbola. Does someone want to tell me what's wrong with this parameterization? And this goes to the heart of why angles are difficult in hyperbolic geometry.
Is it the reason you listed last? It's imprecise because it's infinite.
That's related, but actually, even if that wasn't a problem, even if we didn't care about the practical difficulties, there's still a theoretical difficulty with this. So if I have a point on the unit hyperbola, I can make the x coordinate negative, right, to get another point on the unit hyperbola. But if we have a real number, can this thing ever give us a negative number?
No, it can't.
It can't give us a negative number. So if we look at, let's pull up GeoGebra, cosh theta, sinh theta, it actually only hits one part of the hyperbola. So here, let me share new screen. X squared minus y squared is equal to 1. And then let's get a slider a. And then we have cosh of a comma sinh of a. And let's make a go from like negative 500 to 500. And we'll make, yeah, we'll leave it as speed at 1. Maybe that's too big. Let's go back to 5 and negative 5. We zoom out, see if we can make this point. Wow, it's really out there. Okay, here it is right here. Let's make it red so it's easier to see. No matter how big you make the magnitude of theta, this thing is never going to hit the other side of the hyperbola. I mean, it's fine. The hyperbola is really symmetric. We can just do a reflection across the y-axis to get the other points, but it's not going to behave the same way that sine and cosine does, which are periodic. The periods of these things are actually in the complex plane. And so let's, we'll see how they're related in a second, but this is a very theoretical problem for understanding angles in hyperbolic space. So let's move back to this one. But before I do that, I wanted to prove a hyperbolic analog of Euler's theorem. So we have the regular complex numbers, which mathematicians like to label with this Blackboard C, which are numbers of the type a plus bi, where I squared is equal to -1. And so we had this formula, e to the I theta is equal to cosine theta plus I sine theta, which we got just by looking at how the Taylor series broke down. And then we have their cousins called the hyperbolic complex numbers. And sometimes I've seen people use a Blackboard H like that for them, but that H is actually used for a ton of different things. So, but these are numbers of the form H plus A plus BJ, where J squared equals 1, but J does not equal plus or minus 1. So one thing that you should notice is that the fundamental theorem of algebra is no longer true in the hyperbolic complex numbers, because x squared minus 1 equals 0 has 4 roots. But besides things like that, actually, hyperbolic complex numbers behave a lot like the complex numbers. When you multiply two hyperbolic complex numbers, if their hyperbolic angle is defined, it'll add their hyperbolic angles, and if their hyperbolic length is defined, then it'll multiply their hyperbolic lengths. What we're going to see, though, is that since those things aren't always defined, that sort of intuition from Euclidean geometry does break down. But we're going to see a very amazing band-aid to that solution. So one thing I want to say, though, is that e to the j theta is equal to hyperbolic cosine of theta plus j times hyperbolic sine of theta. So let's prove that. So e to the j theta, we can actually understand is not being exponentiation at all, but just this power series. And so the even powers of n are going to not have any j's, since j to an even power is 1. And the odd ones, we can factor a single j out of it. So we're going to get the sum from theta to the 2n over 2n factorial, as n goes from 0 to infinity. I guess I better write these. plus, and then factoring the j out, we get all the odd powers, and from 0 to infinity of theta to the 2n plus 1 over 2n plus 1 factorial. This is a really nice formula. And I guess I'll just say one more thing about angles in hyperbolic space. The nice thing about hyperbolic sine and cosine is that with the parameterization that we got, we move at hyperbolic length 1 along the hyperbola. So the benefit that we get is that we're moving at a constant hyperbolic speed. The bad thing is that we miss half the hyperbola. So let's say we wanted to find another parameterization of the unit hyperbola that got both parts, or maybe only missed a single point. So we would take this identity, cosine squared plus sine squared theta. If you divide everything by cosine squared theta, you get 1 plus tan squared theta equals secant squared theta, or secant squared theta minus tan squared theta is equal to 1. So this parameterization, it doesn't move at a hyperbolic unit length or unit speed, but it does cover the whole branch. It might miss a single point. Let's see if I remember that correctly. So I'll zoom in a little bit and let's define a new parameterization. Oh, I gotta share my screen, don't I? Okay, so we have, let's say, secant of A, comma, tan of A. Yep, there we go. It's already on the other branch. So the thing about this is it will get all of the points. It just moves at a very irregular hyperbolic speed. So Matthew brought up another potential difficulty with these methods of parameterizing the unit circle and the unit hyperbolic, the unit hyperbola, and that's that we're using infinite sums. So these infinite sums might converge to the functions that we're looking for, but the problem is that practically we can never add up an infinite amount of things. So in practice, you can only get approximate points on these circles. So what is the solution to that? I'm going to develop this. I'm going to develop both theories at the same time. So let's say we have our unit circle here, and let's say we have our unit hyperbola here. And we have both on both of these, we have the point minus 1, 0, and minus 1, 0 here. And we're going to use something called, whose method was this again? I think this was Diophantus's method of secants. Actually, I might check real quick what that's called. Everything I'm doing actually from this point forward is can be found in this book, which was only written like 20 years ago. But Diophantus's method of secants is like hundreds of years old. Let's see. Table of contents. I just want to make sure I'm attributing it to the right person. Yep, it's Diophantus. Okay. And actually, there's not a double S there. So according to Vietas, this book is called Elliptic Functions and Elliptic Integrals by, here, I'll write it down. If you guys ever need to download it, any book for free, I have a website. So I actually downloaded this book and read it several times before I bought the hard copy. It was just so good that I bought it twice. And it's also written by 2 Russians, so you know it's good. Viktor Praslov and Yuri Soloviev, something like that. I don't speak Russian. Okay, so according to Vietta's formulas, if one root of a quadratic is rational, then the other root is going to be rational. So if I have a line going through a point on a circle, wherever the second intersection with the circle is, if that's a rational line going through one rational point, then the other point has to be rational. So with this way, we can get some parameterizations of these unit circles or a unit circle and a unit hyperbola that have some slightly different properties than sine and cosine, but they're still very nice. So if you're a number theorist and you want exact rational points on these curves, this is the way to do it. So this line, we can call it y is equal to t times x plus 1. So if we plug that into our unit circle, we get x squared plus t squared times x squared plus 2x plus 1 equals 1. So if we rewrite this, we get that, here, wait, we got to solve this for x actually. So what we get is 1 plus t squared x squared plus 2t squared x plus t squared minus 1 equals 0. And we want to use Vietta's formulas here. So we have to divide by the leading coefficient plus 2t squared for 1 plus t squared x plus t squared minus 1 over 1 plus t squared is equal to 0. And Vietta's formulas tells us that this is root 1 times root 2. But we actually already know one of the roots for x. One of the roots for x is minus 1. So we get root 1 is equal to minus 1, and root 2 is equal to 1 minus t squared over 1 plus t squared. And then if we want to find the value of y, then we just plug that value of x back into here. So we get y is equal to t times 1 minus t squared over 1 plus t squared minus 1. So we can rewrite that as y is equal to t times 1 minus t squared minus 1 plus t squared. Did I make a mistake here? Minus plus. I'm pretty sure I just made an arithmetic mistake. That should be a plus sign. There we go. So yeah, we get a plus right here if that's a plus sign. And so then the t squareds cancel. So we get y is equal to 2t over 1 plus t squared. Okay, so there is still a defect of this parameterization. So I did it for the circle. How about I'm going to leave it as an exercise for you guys to do right now while I plug this into GeoGebra. Find a parameterization in the same way for the unit hyperbola, x squared minus y squared is equal to 1. And then you still just have to use this same line right here. So we get that I'm going to call this function c of t for circle is equal to 1 minus t squared over 1 plus t squared, comma 2t over 1 plus t squared. So let's go back to GeoGebra. Let's get a new file. Don't save. So we want the circle x squared plus y squared is equal to 1. And then, heck, I'll just include this for when you guys tell me what the other parameterization is. That, and then we want, I guess I need a slider here. Let's call it t. Let's make its max 10 to minus 10. So we have the point 1 minus t squared, comma 2t divided by 1 plus t squared. There we go. And has anyone figured out how to parameterize the unit hyperbola?
Yeah, it's just kind of the same way of the other one, just negative.
Just negative?
Instead of x squared plus t squared times x squared plus 2x, it'd be a minus.
Yeah, so the denominator has a minus sign, and then the x component is a plus t squared.
Yeah.
All right. And we can actually get some famous identities out of this as well. Is that correct? Here, let's draw the line as well. Y equals t times x plus 1. Okay, so we can see that for t equals 1, the denominator of the hyperbola is undefined, so we have to change a little bit. Let's change these points to red and blue so that they stand out more. Okay. So these parameterizations are pretty nice because they give you exact values on the circle, except there's one problem with it. Who wants to see if they can figure out the problem with this one? So one problem, I guess, is that these points aren't moving with constant speed. The larger that the absolute value of t gets, the slower that they move. And that's actually related to the big thing that I want you to notice. The problem is that these parameterizations will miss a single point. They'll miss a single point, and that is the point that we started with, minus 1 comma 0. So it's not that big of an issue because we actually already know what that point is, but these parameterizations will miss a single point. So these parameterizations are still extremely useful for the next thing I'm going to say. But we're going to have to introduce some new definitions to really appreciate why these things are so cool. And then, so let me go back to this. A couple years ago, I did the hard work of solving this in an extremely general case. Let me pull up the formula because I do not have it off the top of my head. Okay, so what if we have, here, let's see, what was the exact variables that I used? If we have a new conic section, ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0, and the point x1 comma y1 is on this conic, then we have that a parameterization of this conic is given by, this is a really ugly formula, don't memorize it, but I'm just saying it works in every kind of conic that you can dream of. Let's see, so et plus ax1 minus by1, I guess that x1 should, I'll move that one down so it's easier to read. 1 minus d all over a plus bt plus ct squared, comma, and then it doesn't look like this thing should simplify to a quadratic, and I probably should have done the hard work to show that it does simplify to a quadratic. We have ct squared x1 plus 2, I'm going to call this thing actually equal to capital T because I'm just going to rewrite this exact same thing. So we have capital T times little t. Capital T includes the denominator as well. Minus t times x1 plus y1. So that thing will actually parameterize any conic of this form. It could, assuming that you have an initial point on it. So the algebra for that is a little bit crunchy, but it's worth your time to do it exactly once. So anyway, now let's get into something that looks like it's completely unrelated, but we will come back around to show what it is. So in mathematics, we want to have good definitions. And if our definitions are good enough, then it will let us prove things for a bunch of different objects at once. So around the 19th century, mathematicians realized that there was 4 common properties to a lot of different mathematical objects. So let's say we start with a set, and then we combine it with some sort of operation. I'm going to write plus, but let's actually write O plus for an arbitrary operation. So a set with an operation with no other assumptions except for it's closed. So if the set, let's call it fancy S. So if A and B are in S, the only assumption that we're making is that A O plus B is in S. If we have an object like this, it's called a magma. Now, let's say we add an identity element. So we add a 0 to it. So if we have a 0 such that, so let's call this the identity. Here, let's describe some properties actually. So there's 4 properties that we could be interested. So I guess the 0th property that we're just always going to assume is closure. And this just means if we combine 2 elements in the set, we get another one. And then we have a property called an existence of an identity. So what we're saying is that there is a 0 element in the set so that any element plus our identity is equal to itself. And we can do it in any order because we're actually not assuming commutativity here. So the second property is associativity. And so we're going to say if we have 3 elements in the set, we can combine them in any order as long as we can combine. I'm going to use the order twice in 2 different ways here. So we can combine them in this order first, or we can combine them in this order as long as we don't change the actual order that they appear in. We can just do the operation in different orders. And then the final property is cancellation. So we're going to say that if A is in our set, then there's also a minus A in our set so that A plus minus A is equal to our identity. So there's actually a lot of mathematical things that have these 4 properties, and we call all of them a group. S plus is a group. So this screen right here is worth your time to write down because this is one of the most important definitions in all of math. I'm going to give some examples of groups in a second, but it's just worth your time to write them down. Let me know when I can move on. You have it in an intro book? Great. We're going to see how groups appear in a bunch of different settings. So can I scroll down? All right. So there's one more property that groups can have, and that's commutativity. It's not necessary though. So commutativity, where we have O plus B is equal to B, O plus A. And if a group has this property, it's called abelian. After a guy named Abel, and it's actually capitalized. It's one of the few names in math that are capitalized. Okay, so let's look at some examples. So the example you're probably most familiar with is the integers and regular addition. You know, it has these four properties. It's actually an abelian group as well. If you add two integers, you get an integer. 0 is the identity element of the integer. Addition is associative, and we have negative numbers in the integers. So if you weakened this to just the natural numbers, then you would no longer have a group because you would no longer have cancellation occurring. So then we have another example. So this is the first example, I guess. Second example is Z mod N under addition. Okay, let's give some non-examples that are related to this. A non-example of a group is Z with multiplication. So can someone tell me what fails in the integers when we're using our operation as multiplication?
0.
Well, no, we have the number 1, so we can multiply by 1, and that gives us back what we started with. And multiplication is associative.
0.
The property 0 is still there. We can multiply two integers and get an integer. And then here, I'm just using 0 for the identity element. So in this case, so we have closure. We have 1 is the identity. Check. And we have associativity. But let's just look at this equation. Can we solve this over the integers?
No.
No, we cannot. So we do not have cancellation. So the integers with multiplication is not a group. All right. So let's look at another non-example. Let's look at Z mod N with multiplication, where N is composite. And we're going to have the same exact problem in this situation because if you have a composite number as your modulus, then there are definitely equations that you simply cannot solve by cancellation. For instance, 2 times 3 is congruent to 2 times 4 mod 6, but 3 is not congruent to 4 mod 6. So yeah, you fail cancellation in this non-example. So two responses to those non-examples are we have the rational numbers minus 0 and multiplication. And sometimes we write a set except for 0, a set of numbers except for 0 as Z star or Q star. Q star multiplication. This one works. Now we can multiply and divide by any two rational numbers. And then also we have Z mod P under multiplication works. So P is a prime number. Does anyone know the proof that you can actually always cancel integers mod a prime? Right. So
Is
if you
it the fact? Oh, sorry.
Go ahead.
Are we assuming it's relatively prime to the to the prime?
Yeah, so I'm gonna have to put a star here. So we're not including 0.
Okay.
Yeah, it
Um,
has to do with the relative primeness.
Well, and yeah, then I guess if you think of like modulus as rotations, then if you're going to have like a certain amount of rotations, like along a, I don't know, as along a wheel with p spokes, you always have to end up at the same like spoke after you multiply it.
Okay, that proof. I see what you're getting at there. Let me just give you a hint for when you see this in a college class, and so you'll know what to do. The Euclidean algorithm tells us that if the GCD of A and B is equal to D, then we can find integers x and y so that ax plus by is equal to D. And then, so let's say that if B is prime, then we get that ax plus py is equal to 1. And then mod p, we get ax is congruent to 1. So then that implies that x is equal to 1 over a mod p. So yeah, this is how you would do it in a college class if you wanted to get full credit on an assignment. So these are some pretty simple and familiar examples. Now, let me look at some advanced examples that we're not going to dwell too much on. Well, actually, here I have a list of examples. I have another example that's easier. So 3. Does anyone know? Wait, did I already label 3 up here? Yeah, 3 and 4. So let's do 5. Does anyone know what an isometry is in geometry? So an isometry is a transformation that preserves lengths. So for instance, the do nothing transformation. This is our identity. Then we have translations. And every translation can be inverted. And then we have reflections. And 4, we have rotations. Altogether, these make up a group called Euclidean geometry. And so if someone asked you what is a geometry, then Felix Klein would tell you that a geometry is a space with a measurement which is invariant under a group of transformations. And this is the modern take on what geometry is, the modern definition. Here, so maybe I'll zoom out a little bit so you can see all of this at once. This is a good example to write down. And I can also scroll up for the proof that multiplication mod p excluding 0 is a group as well, if you want to see that again. I'm recording this one, so I can just send you the notes and the recording as well. There's 2 more examples of groups that I want to give before we move on to the group that we're really interested in. That has to do with the things that we were talking about. I guess I should pay some respect to Mr. Felix and capitalize his last name. We're almost out of time. Time to set thing for 10 minutes. I think I'm going to skip the last two examples because while they are extremely important examples, they're a little bit beyond the scope of what you know right now. Okay. All right. So what is the group that we are interested in? Let me zoom back in so that the PDF is not messed up. The group we care about. Points on a conic. So if I had a circle, right, and I defined, if I had the unit circle specifically, and I defined this point right here, 1, 0, to be equal to our 0 point, and then I have two other points, A and B, how do you think we could define a group of to be able to add these points together? So we want to explore some way of adding points on a circle. What's a way that we could do it?
Adding the trigonometric functions, like sine.
Not quite. We want to add their angles. If we just added the functions, there's no guarantee
Oh,
that
you
we would stay on
mean
the circle.
okay? Sorry, that should mean something else.
So if we add their angles like this, then we can define A plus B to be the point with the sum of these angles, right? And so let's see if we can make the same story work for hyperbolic geometry. Well, if we restrict ourselves to this half of the hyperbola, then we actually can define a group. Where again, we define this to be our 0, this to be A, this to be B. But it's not going to be a group. It's not going to be adding Euclidean angles the way that we would do it. It would just be adding the hyperbolic angles, which don't look the same in a Euclidean sense as you rotate them. So that would be A plus B right here. So if specifically this is equal to cosine theta, sine theta, and this is equal to cosine phi, sine phi, this would be equal to cosine theta plus phi, sine theta plus phi. And then the same story here with hyperbolic sine and cosine. But practically, these groups are a little fuzzy because we don't have exact points except for special values of theta and phi. And it's even more of a messy situation in the hyperbolic setting because now we're locked to 1/2 of the hyperbola. So as number theorists, is there a way that we can fix this? There actually is a very beautiful way that is missed by a lot of people who study elliptic curves. This method is just completely skipped over in a lot of books on elliptic curves. So, notice that these are actually abelian groups as well, which is kind of important. So now let's define just a general circle, like let's just use a general conic. And I'll start with a circle for now. So let's call this our 0 point. Let's call this point A and this point B. And we want to be able to add this A to B only using addition, subtraction, multiplication, and division, basically, so that we get practically exact numbers. So what the idea is you take the line between A and B and you translate it to go through O. Sorry. so that it's parallel here. And then we define this to be A plus B. Okay, so there's a couple things that we're going to have to answer to say, is this a group or not? So if we want to add A to itself, then this is the idea. We take the tangent line at A, and then we translate it here. So this is 2A. And so how are we going to find minus A? Can someone tell me with this operation how we find minus A? All right, so we'll say that O is the identity because, yeah, so closure is guaranteed by the quadratic formula. And so now we have to answer identity, right? We want O to be the identity. So if we take the line through O and A, and then we translate it back to itself and we see where it intersects the circle apart from O, then we just get A back. So O is actually the identity. Okay. And then let's do inverses first, or cancellation. Someone want to try to geometrically describe what the way of finding the inverse should be? Let's see if we can reverse engineer what the inverse should be. So whatever line between A and minus A, it needs to intersect the circle twice at O. It needs to start from O and it needs to end at O. So whatever the inverse of A is, the line between A and A inverse needs to be the tangent line at O. So if we take the tangent line at O and we translate it here, then this will get us A inverse. Does that argument make sense? Okay. So cancellation is given by tangents to O. Okay, now the third one is associativity. And I am going to invoke a formula here. And I'm not going to prove this formula because, oh, you're sad you didn't think of that. You kind of just have to work through what the definitions are a bunch to figure it out. I don't even want to let you guys try to think about associativity though, because it I would be extremely surprised if you managed to come up with associativity. So I'm going to invoke a theorem called Pascal's hexagrammum mysticum. And I don't think Pascal actually proved this, but this is a generalization of Pappus's theorem. So I'll explain Pappus's theorem first. So Pappus's theorem says that we start with a line, or two lines. Okay. So boom, boom. And then we pick points, 3 points on both of them. And we alternate the labels on the side. So I'm going to call this A1, B1, A2, B2, A3, B3. So this is the idea. You connect A1 to B1 with a red line, and then B1 to A2 with a blue line. If this drawing sucks too much, I'm going to move to GeoGebra. Maybe I should be moving to GeoGebra already, but let's see how it goes. And then A1 to A2 with a blue or red line, B2 to A3 with a blue line, A3 to B3 with a red line, and then B3 to A1 with a blue line. So you just alternate red, blue, red, blue, red, blue. Then what you do is you look at the intersections of the red and blue lines. And it's an amazing fact that these three are collinear. Oh, come on. Close enough, close enough. So this is Pappus' theorem. And I'm going to go to GeoGebra for Pascal's hexagramma mysticum because there's no way I can draw this correctly. And I guess we'll do it for the circle. Let's get rid of this. Let's get rid of this. And let's not even look at the background grids because this is true everywhere. So show label, we'll turn that off. So let's say we have 6 points, and this actually works for any conic equation. So let's call this one A1. And this one B1. And this one A2. Oh, I probably have to change my screen over, don't I? No, I'm on the right one. Okay, A2, B2, A3, and then B3. I am running out of time to say the punchline, but so let's see. If we connect this A1 to B1, and then B2 to A2, A2 to B3, B2 to A3, A3 to B3, B3 to A1, and then we got to color them red and blue alternating. So let's see. Red, blue, red, blue, red, and blue. Let's move these so that it's easier to see the amazing phenomenon that happens here. That here, that here. Oh, I might have to keep moving these.
They're supposed to be alternating, right?
Did I not do it alternating? I didn't. Thank you for catching that. Yeah, so that should be blue and that one should be red. All right, that looks much better. All right, so we can see all the red and blue intersections. And we get the same exact phenomenon happening, that these three intersections actually lie on a single line. So I'm running out of time. So I don't expect you guys to prove this, but for homework, I want you to try to prove it, assuming that the hexagramma mysticum is true, that this form of addition is associative. All right, so I have 2 minutes left. 2 minutes left. So what's the punchline to all this? What's the punchline? This is also an abelian group on the circle, and actually we can define the same group on a hyperbola. The same group can be defined on any conic. All right, so, but now we can actually add points on any part of the hyperbola. So if this is AB, whoop. This is A plus B down here. Here, let's make this look slightly better. I know I'm wasting valuable time. Okay, A plus B. So this group is superior on the hyperbola because now you can add all the points on the hyperbola together. But actually on the unit circle, these are the same group. So this method lets you add points on the unit circle exactly. So if this is, let's draw these. OAB, and then let's call this center right here. So we draw this theta phi. So we gotta here, let's do it here so that I have a better idea. So this is theta phi a. Oh wait, we don't want theta and phi in this one. Theta and phi has no place in this group. Here. Whoop. Here A O B. This is A plus B. This is right here, A plus B. This is the same group. And on the hyperbola, it's what's known as a subgroup because there's no way on the hyperbola to add points on this half, but it is still a group on this half. But on the circle, it's the same group. And the identities that I sent you as homework are the proof of that. However, we don't have time to go through the proof, but if you can prove those trig identities, then you proved that these are the same group. Any final questions before I go to my next class? Any comments? Do you want to see the proofs that they're the same group or the other two examples of groups next time, or do you want to just jump straight into the trig identity section? All right. Yeah. This is also here. I'm gonna put in air quotes basically the same as point addition on elliptic curves. It's basically a degenerate case of it, and the yeah. Yeah, it's basically the same as the point addition on elliptic curves. I'll see what I can do to give you the proofs, but we might have to develop some advanced knowledge of geometry with lines at infinity and a bunch of shit like that. So yeah, I'll let you guys go though. I'm sorry we didn't solve any problems today, but I think this stuff is kind of interesting. Anyway, yeah, I need to skedaddle.
All right. Have a good day.
Later.
I thank you.